friends. Let's take a look at the matrix trilogy for the AI students for their potential IA topic. Without further ado, let's get started. Yes, the Matrix trilogy has been a legendary series for the movie avid fans, and I like to correlate that with the AI studies and potential the IA topic. So Matrix in the AI, you get to learn many different fields of matrix, and it actually is a backbone of AI study, along with the statistic and complex number and differential equation. And it can be extended to many things. The first thing you encounter here is the diagonalization, and then the affine transformation for the geometry, and then you get to learn something called the coupled linear differential equation. Okay, so that is great. So for today's lesson, I'd like to go over how these things can be summarized using the matrix. Okay? Sure, so the first series of matrix with Trinity and Neo, I'm going to associate with the diagonalization, okay? So yes, it's in the syllabus, isn't it? It is in the syllabus. I would not take this chance for explaining every bit of diagonalization, but just going over an example and just quickly remind you what it is. It's associated with the eigenvalue and eigenvector, isn't it? So what do you do with the two? So the only thing that you have to do with the algebra of the matrix is a 2x2 case, isn't it? So if I quickly remind you how to do the eigenvalue and eigenvector is to come up with what equation is it? Yes, you have to come up with the characteristics equation of the determinant of a 2x2, where it's a matrix minus the identity matrix, the diagonal multiple of the eigenvalue. And then you solve for the quadratic equation, then boom, if it's factorizable, then what do? We can find the eigenvectors using the linear combinations of these eigenvector, right? So we just try to solve it in just one of them because it's not possible to find the unique solution, right? So then, you can come up with an eigenvector like this. Any multiple of that is okay. You can use eigenvectors 2, 2, 3, 3, doesn't matter. As long as it's parallel, it's fine, right? That's the eigenvector for lambda equal to 5. No problem, easy peasy, lemon squeezy. Let's try to find the eigenvector for the eigenvalue of -1. We did a similar approach, then you can get the eigenvector as such. Any multiple of that is fine. Eigenvector is not unique as long as it's parallel, that's fine. So yes, we got it, right? So therefore, we can have eigenvalue as such, and then eigenvalue and eigenvector as such. So we got the pairs, What do we do after that? Sure, we do something called a diagonalization, don't we? So if I do the diagonalization, it's given as such, right? It's a P matrix and then D matrix, where P is made out of the eigenvectors, and then D is the diagonal matrix made out of the eigenvalues, right? So it's something that you learn in the syllabus. It's not big of a deal, so I would sort of fast forward this, right? It's because you already know this. So yes, for that one, it's called a diagonalized matrix of M with the eigenvalue of lambda and lambda 2, and the only thing that you learn is the two distinct eigenvalues, right? So of course, for the characteristics equation for the 2x2 involves quadratic equation, and depending on the discriminant, it can be positive. So two real roots and two distinct roots equal to 0, repeated roots less than 0. Two distinct complex roots with the conjugate pair, right? So what I'm suggesting here is that what can we extend this? Why do we do the diagonalization? Well, the first application you learn in school in the syllabus is the higher power of a matrix, right? Instead of doing this tedious multiplication, we can now take it into the higher power of the diagonal matrix and then simplify further, right? So for this, we got this diagonalization method, right? So order matters, by the way. So P has to be here, and the P inverse has to be there, right? To call it M. So that's great. So then, one of the applications is the powering it, finding the powers of a diagonal matrix straightforward, right? So that's that. We also learned this in the syllabus for the AI students. No problem, okay? So we move fast forward, no problem. So this is a diagonalized form. Then for that, if you put into the power n, you just have to take the power of the diagonal matrix, then put it into the power on the eigenvalues, right? So if we look at the example of what we just did, right? So we found the eigenvalue and the eigenvector. So we're gonna just put that, right? And then for the powering of that, using the theorem that we learned, this power can now put it into the diagonal matrix, diagonal entries such as 5 and -1. And then if you find the inverse matrix and perform the matrix multiplication, row and column, etc., it can be put it into the simplified form as such. Now you can choose any value of n to simplify the form. Then if you put n equal to 4, you can get the result that you wanted to have, right? Which becomes 209, 208, 416, 417. Easy peasy, lemon squeezy. Okay, so that's something that we learned. But for your IA topic, the first IA topic that I can talk about in this video is your question to start. What about the repeated roots? What about the complex roots. So that's a one example that you can do with this example. But later on, we're going to use this diagonalized matrix for the matrix eigenvalue, eigenvector on the exponential form. That's the main idea that I like to talk about today. We do many things with it. So for the eigenvalue, eigenvector in a higher power, you can do the page rank algorithm. We also use it for the Markov chain. And now for today, we want to talk about the exponential matrix. Okay, what does that mean? Right? So that's something that you do not learn in the syllabus, but I wish they did after teaching you the Maclaurin series, so that you can actually associate with the differential equation, especially the coupled linear differential equation. What does that mean? Let's take a look. To proceed further, you have to remind yourself with the power series of exponential functions. So that's a Maclaurin series of exponential. For those of you who do the AI may not learn, so let me just give you an example. The exponential function can be defined as this power series, where power series is defined as a series that are made of the infinite series of a polynomial. So if you expand the sigma starting with the 0th term, it becomes 1 plus x squared over 2 factorial, x cubic over 3 factorial, goes on and on and on. So this series represents the exponential function. For any perfect square matrix, can be put into the, what is it, the diagonalized form, right? So then it can be used for the matrix power of the exponential function. Let's take a look at what we mean by that. So any diagonalizable matrix A, we define, what is it? We define the A as a P, D, P inverse, where P was made out of the eigenvectors and D were the eigenvalues, made out of the diagonal matrix with the eigenvalues in the diagonal entry, right? But if you apply the, what is it, P inverse and P, then I can do the P inverse P, where I can cancel them out using the identity matrix property. And that will, if I call this as a diagonal matrix, then I can put this as a P inverse e to the power of a P, right? So that is the typical form of the matrix exponential. And so what we can do here is that, yes, this was made out of, what is it? The if this was the matrix form, then using the Maclaurin series, let's take a look. What we can do here is, if that is input for the Maclaurin series of exponential, I'll put that on the x. I'll put that on the x squared. I put that on the, the x cubic, etc. So for that one, if I do the matrix multiple of this twice, if I just quickly show you P inverse AP times P inverse AP, then it gets cancels out. A will be just put onto the power of 2. As you can see, this is what we have, right? And as you can see, this was actually the precise definition of the exponential series, isn't it? So now I can put that as e to the power of a. Therefore, you can see that we can make it into the following diagonal form of the matrix as such, right? So that is brilliant, right? So this is the definition of the matrix exponent, okay? So make sure we are aware of those definitions. So if we want to plug it into our matrix, so you find the diagonalized form, and then we can put it into the exponent form using that. So this is what we had, isn't it? So now what you can do here is putting the matrix will be the P inverse. Here we simply have to put the diagonal matrix here, so then it's going to be e to the power 5 and e to the power -1. So if you do the matrix multiple here with the inverse matrix, you can attain that, right? That's correct. So now we realize what it means by the matrix on the exponential using the Maclaurin series of exponential function. So that's great. So what does it help us? What does it mean? So now we learn not only using the higher power, we can use those higher powers to describe the exponential function, but where is it used for? Well, later on, we're going to see the very method that you learn of finding the general solution of the coupled linear differential equation actually relies on this method, okay? We're going to have a look at that. But before that, we're going to first jump into the affine transformation and come back to the differential equation with the application of this one. But for the second part of the matrix used for the AI students is to learn with the affine transformation extended with the complex number. So let's take a look. So common transformation that is a reflection, the dilation here, and the rotation, right? So those are the things that you learn. And of course, for the AI students, you don't need to know the proof, but it's great to know the proof because one of many proofs that you learn, you get to associate with the complex number, right? So if you want to transform this, initial coordinate by adding the argument theta to go to the image of x prime, y prime, what you see here is you're going to add the argument by multiplying the complex number, isn't it? right? In order to add the argument, you got to multiply the complex number, and if you distribute and compare it with the real imaginary part, where then you can see that this is going to be a system of a linear equation, you realize you can come up with a matrix representation of those rotation, which then can be derived from the one that you already learned, cosine theta, sine theta, negative sine theta, cosine theta, where determinant is 1 for the rotation, isn't it? So that's okay. So, but the reason I show this proof is because I want you to actually realize for the transformation, you can link this trigonometry with the complex number and then put it onto the representation of a matrix. Later on, we can use it for the 3D transformation as well. So, so watch this out. So determinant of rotation matrix is always 1, and reflection is, yes, -1. Very good. Okay, so now can we discuss the 3D rotation is the potential extension for your IA topic as an AI student. Okay, let's take a look what we can do. So that we know is a rotation by the beta, right? And if you want that on the, for example, on if you put the z as an arbitrary axis and you want to rotate by the xy, what you got to do is to only put on the xy coordinate there and put the 0 entries here and the 1 there. Because if you then multiply x, y, z, you see the z wouldn't be transformed, because if you do the row and column here, z is unchanged. However, this product here will change the x and y, but make this, the columns entries 0 and 0 will make the z as a 0, so only x, y are the changed one, right? So for the 3D rotation by the arbitrary axis and then around the plane is this following method. So if you do the algebra again for the, now if I put the x coordinate as the arbitrary axis, and then if you want to rotate by the y and z, you only attack on the y and z axis. So it's going to be like what? 1, 0, 0, 0, 0, and then coco, sa, minus there, right? So that would have been the 3D rotation matrix for this plane, right? So that is great. Yes, as you can see, we can see that, right? So 3D rotation, if you do just the one arbitrary axis, notation is not bad because you're just extending the idea of the 2D, right? But of course, you want to do the, so those are the, the angle of alpha, beta, and gamma with the arbitrary axis of x, y, z, you see? Okay, that's great. And you can do the composite transformation, as we learned from the affine transformation in 2D. If you want to do this consecutively, you often multiply, don't we? So if I do the multiplication of the matrix, it comes like that. Obviously, the order goes from the right to the left, isn't it? 1, 2, 3, okay? But what you realize is that I want you to remember the matrix multiplication is not commutative. If you actually change the order, that rotation is not the same, right? So it lacks the freedom, you see? It's got many arrangement of rotation, and that often creates like the not incorrect, but very different rotation. It's not commutative, but now if you want to rotate by the x, y, z axis, if you do the product, I just did the expanded expansion for you, it becomes like that, which is still a 3x3 matrix. But let's reverse the composite. So if I do x, y, z, I wonder if it's going to be same as a z, y, x, right? So I do the z, y, x, you see? But then you realize it doesn't become the same. If you do the expansion like that and compare with the previous composition, you realize they ain't the same. So as you can see, it is not commutative. Well, for which we already know the matrix multiplication is often not the commutative case. So if you rotate by the x-axis, y-axis, and z-axis, it wouldn't be the same as z, y, and x. Okay, so that's great. So there are many combinations of matrix, transformation, matrix rotation in 3D cases. Namely, there are 12 cases, as you can see. Okay. Sure. And then, so what we can therefore do, what we can do is, what can there be more technique of rotation where I gain more freedom than thinking about arbitrary axis, especially the x, y, z? Can I then choose any axis that is a slanted and then do the rotation at once rather than the composite way as we just discussed? Of course, the answer is yes, right? And for that, it involves with the complex number with a vector, you see? And that becomes very interesting for your internal assessment topic, right? Because we saw one of many proofs, there's a rotation matrix proof using the complex number, right? To show the Eigen diagram spanning with the angle. We use the order form and the multiplication, adding the argument, and somehow put that in the matrix form. How can we do that for 3D? For that, I need another axis that was going to be like working like a fourth dimension, but now in the complex number. And what can we do with it for the rotation matrix is a great start of your investigation, right? Okay, so can we do something similar with the 3D? Interesting vector. This is something called the quaternion vectors, where I, j, k, those are vector, but they're square. I don't know what square that is going to be because I don't know what multiple we're gonna use, right? And if those product and the ijk product with the vectors becoming -1 is called the quaternion. Okay. But here, the example that we want to talk about with this vector is what product is it, what multiplication is it? Because in 3D, the multiplication is not uniquely determined because we learn namely dot product and cross product in the syllabus, right? It's not uniquely determined. Only the ones that are uniquely determined is 2D, as we know of now, also fourth dimension and eighth dimension. The power of the two dimension has the unique, the product. Okay. But 3D, we don't. So which product do we use for this case? Hence, we extend to the 4-dimension case where we introduce, all the product that we learn in the 3D and put it in here. What does that mean? I'm talking in vague. Let me show you an example. So what we call the quaternion vector is the following. We use the ijk as a standard basis. However, we introduce a complex number, right? So the quaternion Q is defined as a sum of a scalar Q naught and a vector Q, where Q1, 3 are made out of this ijk vector as the following. Okay, so that's interesting. It's a great topic for the IA because it can be extended for the, trigonometry and then the affine transformation, especially the rotation in 3D. Okay, so what we should know is not, if you learn something like such as a vector in 3D, for example, you get to learn about the sum and difference of a vector using the diagonal of a parallelogram. Also, you talk about two distinct multiplications, such as a dot and cross product. And for quaternion, as you introduce the new things, you talk about the addition. But what's way more interesting is actually the multiplication. In this multiplication of a 3D case, you get to learn something called the quaternion product here, which I'm going to show you in a second. Okay, so it actually uses a dot and cross product at the same time. It's very, very interesting, isn't it? Because it uses all the product you learn in 3D vector, right? So hence it's uniquely determined, you see. Beforehand, for the 3D case, if I just use the product notation, we didn't know what to do. So it depends on the purpose, right? Finding the angle will associate with the dot product. Finding the area and volume will associate with the cross product. But now for the quaternion, this is uniquely determined, right? Hence, we say this fourth dimension space. Okay, so that's great. Dot and cross product at the same time. And if you ask me, why do we bother learning this? We use all the quaternion vector, and we can put it into the unit vector as such. And this vector, unit vector, can be applied for the transformation, especially for the rotation, right? So if I quickly show you, this means I'm rotating by theta, okay, by the arbitrary axis vector v. For the previous of the 3D rotation derived from the 2D rotation, we use the arbitrary axis on the x, y, and z axis. But in this time, we are using any arbitrary axis such as v, and then we can use any rotation of the rotation angle theta as you wish. And it can be often used for the quaternion space. Right? And it's actually a very interesting, a very important topic for the game developing, for example. Okay, so one of the many rotation techniques that you get to do. So if you're interested in, please get to learn it. It's a very exciting topic because it uses vector and complex number, which is two pinnacle of AI study in topic 1 and 3. Okay, and matrix as well. So another rotation is Euler's angle and then Rodriguez rotation formula. Again, all of them is possible to discussion for the IA and extended essay. So if you're interested in, I really strongly suggest you take a look. The next thing we're going to have a look is the differential equation. All right, let's have a look at the use of matrix for solving differential equation. Okay, here we go. Sure. The most crucial form of a differential equation you learn in IB, especially for the AI syllabus, is either to solve the differential equation using the separation of variable, approximating with the isocline slope field and Euler's method. And then the pinnacle of the differential equation in AI is actually to work with the coupled linear differential equation. In the coupled linear differential equation, what do you learn? You learn about the general solution solved analytically using the eigenvalue and eigenvector, or the approximation of a phase portrait when the eigenvalues are complex roots. But those great mystery of how we can find those general solutions or use of a complex number for the phase portrait can be solved actually having the understanding of a matrix, especially with the exponential matrix from chapter 1 of this video. So I'd like to introduce you a little bit of idea for that, but I will not delve into too much in detail because it will require tertiary level of education and great more knowledge of calculus, maybe something from the AA as well. But if you're interested in, this is just a great sort of a first step to investigate, right? For why such general solution exists, right? So let's have a look. All right, so yes, like the simultaneous equation, sort of a kind, but the differential equation is called the coupled linear differential equation, right? And then those things are often used for the prey-predator equation if it's nonlinear, but we most likely do only the linear, right? So let me quickly show you. This is what it was, right, for the coupled linear differential equation. And what we learned in our syllabus is to find the general solution using the eigenvalue and eigenvector. Let me just quickly remind you about the formula, right? It looks like this, right? But here's the thing. In our study, we never learned why such formula can exist. We never derived it, you see. But some of the other stuff that we also learn for free, and I mind you, please bear in mind, in AI is more focused on inductive knowledge rather than deductive knowledge. The deriving and proving will be emphasized more on the AA study. But for the AI, you don't need to know necessarily why such thing exists, but you need to know how we can use those things appropriately according to the situation, right? I'm not saying which one is better or worse. It's just different. And however, in some of the things, such as in the chapter 2 of this video, we actually derived rotation matrix using the complex number, for example, right? And then we wonder how we can derive this general formula. Would it require too much knowledge, or would it actually essentially be the similar things as we have discussed so far? It turns out it is not that bad, right? So let's have a look at how we can derive this general solution of the product of the exponential, eigenvalue, eigenvector, exponential, another eigenvalue, and another eigenvector. Okay, why? And for that, the chapter 1 understanding is going to be crucial with the diagonalization and then the exponential matrix. So let's have a look. So this was the exponential matrix, just to quickly remind you. Okay, so we already have done it before, right? So that was the exponential matrix, right? So that's great. So it relies on the two things: the diagonalization and then the Maclaurin series of exponential function. Capish? Let's move on. We already looked into it, so no problem. But then I'm going to now go along with the what is a typical differential equation that we solve, such as the equation from the law of cooling, right? The rate of change of temperature is proportional to the temperature itself, right? And that is a typical differential equation where we know the solution already. It's going to be the exponential, isn't it? Because in fact, the exponential function is the only function that is the derivative that has a derivative of itself, right? And if I have for example, lambda mu, it doesn't matter. We can solve this actually using the separation variable, right? So that's what we typically did, and then we know the solution should be the exponential function. No problem, easy peasy, lemon squeezy. Okay. But now what we want to do here is this is a one-by-one problem. This was one-dimensional. What if we move into the n-by-n dimensional space, and then of course now this U as a one dimension will be now extended to the n dimension where it's going to involve a vector, isn't it? It's going to involve a vector, my friend. Let's see what we can do. So now if we represent the n dimensional space vector U vector, then we know that the differential equation will contain in terms of a vector, and all its coefficient can be described in the matrix multiple, right? Right. For example, ax plus by cx plus dy, as we are already aware of, can be described as matrix multiple with the 2 by 2 and 2 by 1 matrix, isn't it? Same thing for the differential equation. I can say the derivative. If I have such differential equation with the vector, I just simply have to represent with the matrix, which is going to play like the constant coefficient. Easy peasy, lemon squeezy. Okay. Then we wonder, okay, well, what do you think the solution is going to be, right? Would it be drastically different from what we already have done with the one-dimensional space? It turns out it's not that bad. It is actually not that bad. It's actually going to be also given as an exponential form, right? And why is that? Well, because we already defined the matrix, exponential matrix, we're using the power series. And if you actually put the exponential matrix here and then try to differentiate the term one by one using the chain rule and the group by the A, you realize it works like the typical typical differentiation as we did for the exponential function. Just a comes out, where a now in this case is not a number, but it's a matrix, but it's not a problem, right? It can be defined, right? So that's beautiful. That's the beauty of the exponential matrix, or any definition. If you define it well, it needs to follow the typical property, such as the if you multiply, the linearity will be preserved, as well as the derivative becoming itself. Okay, that's beautiful. That's beautiful. So in fact, now we can generalize, if you have such differential equation where things were given in vector and the A is a matrix, right? It's going to be given as the solution is going to be given as the exponential matrix, right? So that's great. So if that is the differential equation in vector, and again, that is solution is going to be also given in exponential. However, the input is going to be in the matrix form. So that is great. That is beautiful, right? So where we know using the diagonalization, sorry, it's supposed to be P and P inverse here. My bad. And that's the matrix, right? That's why your general solution was given as such, right? Remember, this was the general solution of, for example, if I had a dy over dx was let me try with this. Okay, let me try. If your differential equation was dx over dt, dy over dt, given as a vector, and then we describe this as a and then the xy, right? Okay, where x and y are the functions in terms of t. And then, as you can see, now we know, okay, the solution here, in fact, is going to be, what is it? Exponential matrix, AT times whatever the initial conditions, such as x naught and y naught, where that can be put into the, so that is a constant multiple, so it's going to be a matrix multiple. It's going to be, therefore, where that guy is going to be, described by the p e to the power of v t, right? P inverse, and I'm gonna do that matrix multiplication with the x naught and y naught, where P matrix is made out of the eigenvector. So if you expand them out, you can see that such general solution would come out. You see, after having done this as a 2x2 matrix, and you just do the linear combination, then we're good to go, right? So it's not that bad. You see, it's definitely derivable. But then for this, the such deriving method was not seen in any textbook is because it requires your knowledge on the power series of exponential function, and you do not learn that in AI but AA. But it's quite unfortunate because it can open a whole new horizon of starting with the AI and differential equation, especially dealing with the couple linear differential equation. So that's great. So another example is, what about the complex roots, right? Because when you learn the complex roots, you do not learn the general solution. We only talk about the phase portrait, right? About whether it's a center or a spiral in or a spiral out. You see? Sorry, unstable spiral is the one that goes out, right? Or the stable is going to be one that goes in, right? So we only talk about the phase portrait, but we never learn about the general solution. But now, having acquired that the solution can be in exponential form, we can actually derive the general solution. But it will involve quite a few algebra. So, let me quickly show you. So now I'm willing to put those things in a complex number for the general solution, right? No problem. And let me come up with an example of a couple linear differential equation and see what we can do. So let's take a look at this couple linear differential equation with such matrix. If you just do, the matrix multiple, you can see that differential equation is going to be like that, right? So it says my function's multiple, derivative is itself, and then what is it? The derivative will be the negative multiple of itself, right? And then we wonder what function this is going to be. Let's take a look. Oh, sorry, not itself, but it's a vice versa, right? And then the typical one that I can see, if I let this to be, for example, xy and becomes the y prime and negative x prime, changing vice versa, it reminds me of what function? Out of the elementary function, polynomial, exponential, logarithmic, sine and cosine, and the one that I can kind of guess is the sine and cosine, isn't it? Because if you had the y1 as a sine, its derivative is cosine, where cosine's derivative is negative sine, you see? It matches, right? So we sort of know the solution already, but we want to be able to derive it actually using the general formula. So let's try that. So now let's try to solve for the characteristics equation and find the eigenvalue and eigenvector. And then I already found it for you. Your eigenvector is just I and negative I. And your eigenvector will also be given a complex number. You only have to find one of the eigenvector because it's going to be conjugate pair as well. So it's not that bad actually. So now I found the eigenvector as 1, negative 1. then the second eigenvector must be conjugate of that. It's going to be 1 negative I. No problem, right? So then for finding the general solution, I need the exponential matrix, isn't it? So I put the exponential matrix as such, where I can put this in the diagonal matrix. Kumbaya, I've just done the computation for you. Follow me, no problem. So if I do that, what do I get? It's going to be given as the following matrix, okay? And then for that one, it's going to be in the multiple with the initial condition, right? But as you can see, in fact, this is the one matrix. Very good. This is actually rotation matrix, right? Because if you put the determinant, it simply just becomes 1, right? So that is great. So now the solution was given in terms of rotation matrix, but with using the initial condition, if I multiply by 1 and 0, then I get the following solution as expected, you see? So that is brilliant. That is brilliant, okay? So if I put the negative sign, so look, if I differentiate the x, then I get negative sign, which becomes the y. If I differentiate the y, which was negative sign, it becomes negative cosine, so that's going to be the negative cosine, right? So it is a solution. So we can solve it now, even if it's a complex eigenvalue eigenvector, I can still generalize it using the general formula, thanks to the exponential matrix. Easy peasy, lemon squeezy. Okay. So more general solution, but you know what we had, you know, was just purely imaginary. It was plus minus I. But if you have a, you know, as you remember, if you have a, what is it, the real parts, depending on the sign of the real part, it's gonna be unstable spiral or it's gonna be a stable spiral, right? Because if it's a positive real, it's gonna diverge. If it's a negative real, then it's gonna converge. You see? But why? You see? Now you can not only see the phase portrait of it, but also the general solution of it. So let's see what we can do. So if I have a, you know, complex eigenvalue of conjugate pair, you can have complex eigenvector, which is also conjugate pair. So, you know, let me just quickly derive the general solution here, where the eigenvalue was p plus rho plus I omega, then it's going to be conjugate. She's also given. So imagine my eigenvector was also given, okay, here. So now I put the eigenvalue here, see? And then I put the eigenvector as such, okay? But I just group by the real part, the imaginary part. I actually skipped a lot of parts here because I just wanted to do the favor for you. I got the real and imaginary part separately. Okay, have I? No, I don't think so, right? Give me 1 second. No, I think I grouped by the, sorry, I think I grouped by the, what is it, the eigenvalue here. So now I still have the sum of the eigenvector and the imaginary part of the imaginary number multiple of eigenvector. No problem, you know. Then, you know, I have written it thoroughly so you can actually see on my PPT, but using the sum of complex number and conjugate becoming the purely real difference is going to be twice of the imaginary part times I, etc. Simplification can be made more. So if you see, the general solution is actually going to be given as such. Okay, you don't have to know this. Don't worry about it. But if you actually are willing to talk about the couple linear equation that involves complex eigenvalue for your IA topic, maybe deriving using the matrix would be very, very nice, very, very beautiful. But as you can see, this is the general solution, right? This is going to be the general solution with the eigenvector 1 and eigenvector 2, you see? And as you can see, look at this. But that's great. So now we got two things that I got to be worried about for the complex eigenvalues. I have exponential growth and decay depending on the sign of p, but also I got sinusoidal behavior on my general solution. So it's going to be somewhat periodic, right? But depending on the p, maybe my amplitude would, you know, converge. It's going to converge to 0, my amplitude. But if p was a positive, maybe my amplitude would diverge. If p was a 0, it's going to be purely periodic, right? Purely sinusoidal. Hence the standard solution, right? The one that is stable. So now you can see from this general solution why phase portrait was given as such, because your general solution for the eigenvector are going to be product of exponential and then the sinusoidal, right? That is great. So now if I put that idea into, for example, so that's the final stage of the simplification. As you can see, just eigenvector with the product of exponential sign, eigenvector product of exponential and the sinusoidal. But so if I come up with that example with the given as eigenvalue as such, eigenvector as such, I already have done it for you, right? So don't worry about it. If I just derive the general solution, it looks like that, okay? And as you can see, you know, it's going to be, what is it, unstable spiral because I got the exponential growth, you see? But then now, you know, for the general solution, it's going to become like the sinusoidal first. But then as you can see, because I'm multiplying the exponential growth, the amplitude is going to get bigger and bigger, and it's going to be unstable like that, right? That is great. So if I quickly, for example, demonstrate here, we only learned this, don't we? We only learn about the phase portrait depending on the sign of the positive real, but as you can see, if you look at the general solution, realizing that it was always a product of the exponential and the sinusoidal for the general solution of the complex eigenvalue eigenvector, you see why the spiral will be given if the real part is negative, because you are multiplying the exponential decay to the sinusoidal, right? That is great. If I quickly also show you the positive, right? Sorry. If it's a positive real, then it's gonna be the real part is positive. It's gonna be spiral out, unstable spiral. As you can see from my sinusoidal, my amplitude is gonna diverge. That's why it's gonna become chaotic, right? And if I quickly again see the real part being 0, then it's gonna be purely sinusoidal. Hence, you have a solution center, right? It's gonna be purely sinusoidal, right? That's how you get to actually understand more about the phase portrait based on the general solution if you understand thoroughly about the eigenvalues being complex numbers for the couple linear differential equation. To fully understand that, you need to have understanding of exponential matrix, right? Right, that really encaptures everything I wanted to talk about today, right? I want to talk about the potential use and application of a matrix for your IA topic as an AI student, because matrix has a great utility, right? It talks about the diagonalization, which you can use for a lot of computer algorithms, and then also if you extend to the idea of exponential matrix, you can generally deal with the differential equation of a couple linear differential equation for a starter today, right? But you can also use it for example, second order differential equation. You can use it also for the inhomogeneous differential equation. It's quite marvelous. And you can also extend it for the calculus, such as a partial derivative, and talk about the Jacobian matrix and why we have such matrix. It's great. And for the again geometric interpretation of a matrix using the affine transformation, we were only limited in the 2D in our study, but you can extend it to the 3D. But then it's sort of a synonymous, it's a simultaneous sort of understanding, because even for the 2D rotation matrix, we use the complex number, right? And it can do the same thing for the 3D, introducing a new interesting vector such as a quaternion vector, right? And again, that is going to capture your understanding with the matrix, trigonometry, and vector and geometry. It's beautiful, beautiful. But yeah, so those are the potential topics. If I get more insights, I will always be willing to share with you. All right, but that's pretty much it for me today. Okay, I will see you next time. Thank you. If you haven't watched The Matrix, watch it. It's a great movie. Analyzable will be then P, D, P inverse. 모시모시. I'm filming. You will.